Hello, welcome back. This is, I guess, video number 3 of 4. This is the second one in our series on concave mirrors. So this one, make sure that you've got a pencil and paper if you're trying to sketch along with this. Get your ruler out, that kind of good stuff. It'll help. And this is the big part that you're going to learn how to do these ray diagrams. So the part that I'm doing here, I'm going to be doing kind of way too fast. And I know that because I don't want this video to take all that long. But this is a big part of what we'll be practicing in meet number 2 for this week. So anyway, being able to kind of figure out where an image is going to be formed from a concave mirror. So you can see on the picture right here, there's an actual lab setup. I've done this lab a bunch of times with students where you've got a little concave mirror. The mirror is in this little stand over here, right over there. Then you've got a candle in front of it. And then there's an actual screen behind it, a piece of paper that's actually showing the real image that's being projected onto that screen. Notice how the image is inverted. And you can kind of tell from the distances there's something different that's going on here. So take a look at how close this mirror and candle are together versus how close the mirror and the image are versus how close this candle and image are, or candle and mirror are, and how far away now this is. This image is quite a bit further away, and then the image is more magnified, it's quite a bit larger. So how do we figure out, how do we predict where an image is going to be based upon the setup of a mirror of known shape and an object, and if we know where the object is? So this is using ray diagrams. So it's basically a graphical or geometric approach towards identifying the location of an image. So with this, graphically locating this image. I know this looks, oh my God, right? There's so much going on here, but you can hit pause and come back and check this out. So what's going on in this image right here is that we have a couple of different things. So number one, here's our mirror over on this side. So this kind of ghost looking thing is over here. I am going to strongly suggest that when you draw ray diagrams, that you put a little ghost mirror line. That's what I call this thing. And this is not a real thing. Like I said earlier in the last video, when we draw curvature like this, it is way too extremely curved. And most of the time when students try to replicate ray diagrams like this with a super curved mirror like this, the lines are going to cross right. They're going to end up in an incorrect spot, and it's going to be really confusing for you. So what I would really like you to do is at the intersection of the principal axis, again, which is this horizontal line, or kind of horizon, at the intersection of the principal axis and the mirror, I want you to draw that kind of perpendicular mirror line to it. And it's not a real line, so I just have it done in a dash line here. And make your rays go there. So I would not have them bounce off of here. I'd actually have them come all the way through this spot. Again, with student drawings, I've seen this over and over and over again. If you try to extend your rays only to the edge of the mirrors are so distorted and so overly curved in student drawings that it's going to throw off your drawings, and it's going to make it a lot harder to interpret. So second thing, okay, we've got kind of our physical setup, mirror, principal axis. We've got our main geometric points, right? Oops, sorry, I didn't mean to move that out of the way. We've got our main geometric points here, which would be things like C and F are listed on here. So our center of curvature, our radius, right? We've got F, or our focal point, is here. We've got our mirror line and our principal axis. Those are kind of the key things that we need to have on there. Next thing is, so our object right here is located out kind of far away. It's not off at infinity, so not all of our rays are going to pass through the focal point, but it's past C someplace. It's somewhere just kind of out there. So like this is a pencil. Whenever you draw objects, make sure that you draw some sort of an object that is not quite symmetrical. So draw it like an arrow. A lot of times I draw trees, something along those lines. Don't just draw a stick, because if you just draw a stick, it's really hard to know if your object is right side up or upside down. So make sure to kind of draw some sort of an object. So we have a pencil right here. Again, pencil is placed kind of out beyond C. It's kind of further away than the center of curvature of this particular mirror is. So now there are 3 rays that we're going to draw. This is part of our conventions for drawing ray diagrams. I'm going to ask you to do this. This is exactly what I'm going to ask you to do in a performance assessment, is to draw me by hand one of these ray diagrams. Some people I know draw these on computer. I would like you to practice drawing them by hand for the performance assessment, so that you don't just copy and paste them from the internet. I know how that works. So anyway, again, practice using your skills a little bit. If you're really good at CAD drawings and things like that, we can talk about it. So anyway, 3 rays. Look where ray number 1 is. So there's a pattern to this. Ray number 1 starts at the tip of the object. So they're all 3 starting at this top part up here. We could pick any spot that we want. We could start at, the eraser, we could start at the middle, but usually when we draw these, it's usually at the top end of whatever that object is. So ray number 1 comes in parallel to the principal axis. just like the raised diagrams that we saw in the last kind of diagram, parallel to the principal axis. And from that, any ray that comes in parallel to the principal axis will reflect through F. This is the definition of the focal point. Any parallel rays to the principal axis will reflect through F. So ray number 1 is always parallel to the PA, and then through F is where that goes. So that's the first ray that you're always going to draw. So ray number 1, bam, hit it on there. So lay your ruler out, make sure that this line and this line are parallel, and then, and I would, again, if I were you drawing it, I would go all the way to here and then draw it back through there. Go through F that way. Again, in student drawings, that's the way to make them work. I promise. Trust me. So anyway, in parallel to the principal axis and then back through F. Okay, ray number 2 is kind of the reverse of that. So ray number 2 starts at the same spot. Now it's going to go through F, and instead it'll bounce back flat. Again, anyone that comes in parallel will go through F. The reverse is also true. If it comes in through F, it'll go back flat out. And so you can kind of see where that one comes down. Again, you line it up from the tip of your object through F, extend it all the way to the mirror line here, and then reflect it backwards. So this one is through F and then back parallel to PA. Okay, third ray is actually a really straightforward ray. The third ray is basically along the normal line. What this is this is the ray that's going to basically go straight to the mirror and straight back. This line is through the center of curvature. That's what the definition of the center of curvature is. So ray number 3 goes through C to the mirror and then bounces back through C. Basically, it's perpendicular. It's straight on into the mirror because it's going right directly along one of those radii kind of lines. So again, line up your ruler from the tip of your item through C, and that's an easy one. The last thing that I want to add to this, and it's not shown in here, but this is going to help us later on if you get into the habit of this one. I wanted to grab a diagram that didn't get too huge. The third thing that you need to kind of draw in here is these guys. There are reflected rays that are virtual. And I want you to kind of get in the practice of drawing these. So just like we did with the plane mirrors way back when we had an incoming ray, the reflected ray bounced straight back to the object, but also extended behind the mirror. It's always the reflected rays that extend virtually behind the mirror. So in my drawing, I'm going to add these to what's on the screen right now. So this is an incident ray, so it would come this way, but it's the virtual ray that would extend this direction. For the second ray number here, there's the incident ray and the virtual rays going out. So the virtual ray would extend that way. And then for ray number 3, this one would literally just kind of continue all the way down through here and then go that direction. Okay, so why do we do that? As we get into the third video when we're drawing virtual rays, virtual objects, this becomes a critical skill. So this should be something that you draw in every ray diagram. You draw the real rays, the ones that are reflecting back with solid lines, and then the reflected rays you continue behind the mirror with these virtual dashed lines to indicate that those are virtual rays. And in this case, yes, these virtual rays all diverge, showing that the virtual rays do not form an image. So where is our image? You can see it clearly in there. It's where the real rays cross, and it's not the incident rays, it's where the reflected rays cross. Right there is where you're going to get the mirror image, literally, of your original point. So if it was the tip of the pencil, that's where they place the tip of the pencil where those 3 reflected rays have converged. And again, this pencil now, you can kind of see it. Some of the characteristics of it, it's upside down, right? And it's a little bit smaller. So we'll take a look at this in a second. So this is graphically locating an image, the 3 rays. You will always draw these 3 rays. So again, to practice without all those things on there, if you want to, if you're watching this video, hit pause. You can kind of sketch this out really quick. Again, there's your principal axis. You can plot C and F. Remember that whatever this distance is, C should be twice as far. So if you're just making one up, make sure that you kind of plot these 2 points sort of carefully. So if this is like an inch on the piece of paper, make sure that this one's 2 inches away on that piece of paper. If you don't do that, your drawings are going to be really funky. So again, remember that C is the same thing as saying 2F. Those are the same distance. You've got your curvature for your mirror right here. And then again, I've kind of drawn my straight line, ghost line, so I kind of can not screw up my drawings a little bit more easily, right? So ray number 1, Again, mine's going to look bad because I don't have a ruler. It's very hard for me to do a ruler with this graphic tablet that I use, so my apologies on there. So ray number 1 comes in flat, so I'm going to try to draw it as straight as I can. In flat, there we go. And then it's going to bounce back through F. So this is the incoming ray like this direction, and then it's going to bounce back this way, something like that. And then my reflected ray is going to go back that direction. Okay, ray number 2 goes through F and then bounces back flat. It's the mirror image of this one, right? And it's the opposite in terms of its pattern. So this one's going to be harder for me to draw, but let's see what I can do here. So in through F, kind of like that. And then it's going to try to bounce back flat, kind of, sort of. Yeah. Wow, this one definitely did not get parallel, did it? It kind of is swinging downwards, but you want it to be parallel if you can. So make sure you check carefully when you're doing it with a ruler. And this one is obviously not going to be the right spot. I've done something really, really markedly wrong. And then C should be like this, where you bounce it through. I can totally see what I did. It can bounce it through like this through C. It would go back down here, and then it would bounce back straight along that same path. So this is both an incoming and outgoing, and my reflected ray would go through. Oh, I forgot my other reflected ray. There we go. So there's my 3 rays. Okay, so you can tell, like I said, for me drawing this, I kind of did blah. This line here going down flat is part of my issue. So probably what it is, I'm going to kind of fudge mine here just a little bit. I am betting that my angles are off just in how I do that one because that's the hardest one to draw. It's going to come back kind of this way. It should be more like that. That's what it should be. Again, if you're doing this with a ruler and not trying to freehand it on a screen, it's a lot easier. So where those 3 lines line up, again, is the point where my arrow would be. So if I was going to draw my object or my image would be like right here is where it would be, like that. So there we go. So that would be my little upside down arrow. And you can kind of see, again, kind of where it is and kind of where it's physically located. So right now it's smaller, it's upside down, right? And it's a little bit closer to the mirror than the original object was. So let's take a look at this in terms of being able to describe now where our image is. We're going to practice using some of these conventions that we kind of talked about, introduced in a unit video or 2 ago. So we're going to talk about DI-DO, HI-HO, and M is our new one that we're going to talk about now. So DI and DO, distance to the object and distance to the image. So take a look at where DO is. DO is from the mirror to the object. So this to here would be considered to be DO. And from here to here, right, this little dot would be DI. So again, DO and DI. So with these, DO is always given a positive value. And when I talk about sign conventions here, I'm talking about positive or negative signs. If you've got a ruler, you can actually measure those distances. And we do some magnification things. Using a real ruler will certainly help. But you could tell me that DO is always considered to be positive, wherever it is. By convention, if it's a real image, and this one is a real image, the distance to the image is also considered to be positive. So if DO here is, plus 15, then DI, I'm assuming like this is 5, this is 10, this is about 15, then DI would be considered to be about plus 7 or so, something along those lines. But again, they would have the same signs. DO is always considered to be positive. DI, if it's a real image, not a virtual image, it's also considered to be a positive distance. Okay, HO and HI. So height of the object goes from here to here. How tall is that? Let's say this is 10. I don't care what it is, some number. We would consider the height of the object to be positive because typically it's an up thing. You're not doing something upside down or something weird along those lines. But if you take a look at the height of our image, there's a couple of things to note about this. Number 1, it's smaller, and number 2, it's upside down. So maybe it's something like that. It's only 5, half the height. But the height of our image, because it's upside down, we're going to use a negative sign for this. And this is important. Again, HI, negative, means that it's inverted. And you could just take a ruler and measure it if you want to do that. But the negative sign tells you that it's upside down. Again, the positive sign of DO tells you, or DI tells you that it's real. It's a real image. But the negative sign of the HI tells you that's an inverted image. Okay, magnification is what this thing stands for. Is the object bigger or smaller? And you can take a look at it. You can tell just by looking at it that's smaller, right? So with this one, our magnification here, there's 2 different pieces of information in here. Number 1, our magnification is less than 1. If you had a magnification of 2, by the way, it would say that your object was twice as large. A magnification of 1/2 would mean it would be half the size. And just looking at this, it's approximately equal to magnification of 1/2. Right, roughly. Again, we don't need to worry about the exact values to it, but approximately 1/2. It's less than 1. It's not greater than 1. The second thing is here that the magnification is negative because it's inverted. So magnification less than 1 means it's smaller or reduced, you could say it that way, and it's inverted. So we could say something like the magnification for this is like negative 1/2 is how you would write those things together. Negative sign here meaning it's inverted, 1/2 here meaning it's smaller in size. Again, if you had a magnification of +2, it'd be twice as big and right side up. Magnification of +4, 4 times as big, and something like that. Magnification of -1/4, 1/4 the size, and upside down. So again, magnification is M, and that gives you some idea about not only the size of the image that you've got, but then the orientation of the image. So the orientation of the image is both in HI and in M. The size of the image, in terms of its size, is given to you in both HI and M, and then the distance in the image is given to you in DI. Okay, going along with this, there is math that you will need to do. I'll have you do like 1 or 2 little math problems on this, but you can copy these problems down, these little equations, and use them. There's a way, if we're trying to mathematically locate an image, there are 2 little formulas, mirror equation, magnification equation. I am focusing more on the graphical thing because I know y'all can do math. I bet you're pretty tired of math by now. But you can kind of deal with these math equations, and they're not super bad. One of the things that's weird about the mirror equation, and this works with any kind of mirror, is that you have something called this particular thing helps you locate where the object is going to be. And it's 1/f. Remember, f is focal distance, whatever that is equal to 1/do plus 1/di, or di/do, doesn't really matter. Distance to the object plus distance to the image. The only thing you got to be really careful with is to be really careful of your algebra. Because these are fractions, you've got to be a little bit cautious. What I really strongly recommend you do in your homework problems that have you use this equation, just use them as decimal places. And then if you're trying to figure out what 1/f is, use this button on your calculator. That's the x to the -1 button. That'll give you the 1/, and you may have an actual button that has that too, just depending on your calculator. So you don't have to try to leave these as fractions or complicated fractions. Put them in decimal place form. Like if I know that my DO is 5 and my distance to the image is 2, I don't need to find least common multiples for this. I'm literally going to go 1 divided by 5 plus 1 divided by 2 equals, and then I'm going to hit the inverse of that answer. So just flip it over digitally. Don't worry about trying to do it in fractions. Say, I'm not a math teacher. I don't really care. I just want the actual distance for what the focal distance is. Second equation is the magnification equation. You can use this to figure out how large or small an object is. And so for this one, the easy way to remember it is hi-ho, di-do. Hi-ho, di-do. The only couple of things in here to kind of keep in mind about this particular equation is you can use either part of it. So you can either use like this half of it if you want to. You can use, this half of it if you want to, like this part. If you have those pieces, you can use those in and cross multiply. Or you can use the other version of it. Come on, give me my pen. There we go. Where you could use M and dido. So you could use like this and this, really this and this together. There we go. Didn't know I could make that picture smaller. Learn something new. So M equals negative dido. Why is the negative here? Okay, the thing that's important about some of this stuff is to make sure that you're assigning signs correctly to your di and do. So the magnification, in order to get the right number sign or the right value to this, whether it's positive or negative, you might need to add that negative sign into this, di, do. Again, remember, real objects are both going to be positive. HI and HO, one will be positive and one will be negative. So in order to get the sign correctly, that's why this negative sign is in here. So it's important to pay attention to negative numbers in there. They are directionals, but they are kind of mathematically important in here, especially more important as we get to virtual images. So there you go. Your 2 equations, the mirror equation, 1/f equals 1/do plus di. I like dido by myself, but 1/f over 1/do plus 1/di. The magnification equation is hi-ho dido. Magnification equals height of the image divided by the height of the object, and equals negative distance to the image divided by distance to the object. So again, 2 different equations to allow you to mathematically predict where it is and sort of match it to a graphical version. Again, I'm having you focus more on the graphical side of it because I know you don't have a lot of experience with graphical drawing. I'm trying to help you build a skill set. So there you go. So that's it for today. A little bit long. Sorry about that. I apologize. And I hope you're not too entirely bored. On meet number 2, we'll practice doing a lot more of these ray diagrams. So I'll see you when you tune in. Have a good day, guys.